Also, another round of applause for Evan and Jason. Thanks for having me. I'm really excited to be here. SeattleJS, long-time listener, first-time caller. So I'm excited today to talk about the browser crypto APIs, the cryptographic APIs in your browser. And I work at Microsoft. We'll talk more about that in a second. So what are we going to do today? So first, use a QR code and a URL for my slides if you want to follow along at home. So first, just briefly introduce myself. And then we'll talk about what are you going to learn, why am I here? And then we'll do kind of a glossary. So we'll kind of do like a crypto 101 for those of you maybe who have not done crypto stuff before. Help set the table for the rest of the talk. Then we'll go into the actual APIs themselves, give an overview, and then also some concrete examples. And then we'll do two case studies. One is the Microsoft Security Response Center and MSRC, and then the other one is Microsoft Authentication Libraries, which is what I work on at Microsoft. And then at the end, we'll do some learnings and some additional resources. So like I said, I work at Microsoft. I work in Azure Identity. So that's part of all the identity services at Microsoft. So Azure Active Directory, most namely. Chances are many of you or your companies use Azure Active Directory. So I work specifically on developer experience on the authentication libraries. These are the open source SDKs that allows you to integrate with our identity services, both in terms of Azure Active Directory, so that's like a Microsoft login screen, but also our things like our identity white labeling services, or white label identity services. And I'm also a guest lecturer at the University of Washington where I teach web development in the information school. So why am I here? And what are you going to learn? So first is to raise awareness. When I first started working on these APIs, I did not know they existed. I've been doing web development in JavaScript for a long time. And so I was kind of surprised at that. I talked to a bunch of other developers I know who were also very experienced and they also didn't know about them, let alone have used them before. So I wanted to get more people aware of their existence. Give some practical use cases, like I said, so demonstrate how you can use these APIs to solve real world problems, not just build like proof of concepts, but actually solve real world problems for your business. Share some learnings, things that we've learned from using these APIs. And then inspiration. So hopefully after all this, maybe you can think of something that you can build in your products or improve in your products using these to build more secure experiences for your customers. So we'll go kind of like a quick Crypto 101, might be a review for some of you, but for some of you maybe not. So what is encryption? So this is from Wikipedia. Encryption is the process of encoding a message or information in such a way that only authorized parties can access it, and those who are not authorized cannot. So it's basically, move to the next slide. So kind of the terms here are, you take data, or plain text, as it's referred to, and it's transformed by an encryption algorithm, also known as a cipher, into a format that is unreadable to the human eye, and is hard to guess for machines, and this is a ciphertext. It's not impossible, right? You can try to decrypt something for thousands of years and maybe you'll get it, but in theory it's not. Data is encrypted by the encryption algorithm using a public or private key. We'll talk more about that in a second. And then data is decrypted by a decryption algorithm using one of the keys used as a private key. So how this will work is for an encrypt something, here's a plain text, a social security number. We'll add a key, we'll take that and the key, and we'll provide it to the cipher, the encryption algorithm, and we'll get back our ciphertext. So that's alphanumeric string that you can't read. And if you want to decrypt, you do the inverse. So you take the cipher, take the key, give it to the decryption algorithm, which is also a ciphertext, beginning, and then you get the plain text back. That's cool. So there are two types of encryption strategies, symmetric and asymmetric. So in symmetric encryption, you have a single key, private key or secret key that is used by all parties for all operations. So encrypting and decrypting uses the same key. The private key must be stored and transmitted securely by all parties. So if you have two systems and you're going to have a shared secret where you do this, you're not supposed to just email your secret key or put it over Instant Messenger or Slack or whatever like that. That's technically not really secure. So you don't want that to be compromised. one of the things is it's performed for large amounts of data. You'll see an application of this later, but symmetric encryption is much more performant for like large files than asymmetric encryption. And then data is encrypted and decrypted with private key, which is, as we just said. And then for digital signatures, we've also talked about data is signed and verified using the same key. So again, same key, all operations. For asymmetric encryption, there will be scenarios where it's either impossible or impractical to share the secret key between two systems. Maybe you have a large network of many different services, and you can't securely transmit your private key to all these different systems, and you want them all sent. You want all of them to send you encrypted information to you. You can't do that if you can't give them the secret key. So that's what asymmetric encryption is for. So instead of a single key, you get two keys, public and private key. You've probably done this before when you like set up Git and stuff like that. So the private key keeps secure, and the public key does not have to be. So you can give that public key to anyone, in theory. And then for encryption, you encrypt data with the public key, and then you decrypt it with the private key. So what you can do is if you have a system, you want some other system to send you encrypted information while you can read, you give them the public key, they encrypt that data with the public key, they send it to you, and only you, who has possession of the private key, can decrypt it. And then for digital signatures, data is signed with the private key. So if you want to be able to send data to another system and have that system be able to verify that it wasn't mutated during transit, you sign your data with a private key, and then you give them the public key, and they can verify that signature. We'll talk about that right now. So digital signature is a mathematical scheme for verifying the authenticity of digital messages or documents. From Wikipedia again. A valid digital signature gives the recipient a strong reason to believe the message was created by known sender and that the message was not altered in transit. So in encryption, when you look at your data, you can't actually see what it is, right? You just see a random alphanumeric strings. You can't actually see that it's a social security number. Well, digital signatures, this is for scenarios where it's okay for the data that you're sending to be visible to someone else. So data is transferred to, so this is for things like access tokens, for example, and OAuth, which is what I work on. At Microsoft, our OAuth tokens are not encrypted, they are signed. So you can look at the OAuth token, you can see the claims inside of it and things like that. But in order to use that token, it has must have a valid signature. And only the services within Microsoft can create that valid signature. So the data, like an access token, is transferred along with the signature that the recipient is supposed to verify. That signature, that recipient might be another system, it might be you. You might be giving something a token and having them send it back to you. The signature is computed by the sender using a private key, so that's you. And it is verified by the receiving party either using a private key if you're doing symmetric encryption, or the public is verified with the public key for using asymmetric encryption. Like I said, a valid signature can only be created with the private key. So if the data's been altered, the signature verification will fail. And that's how you know that that was not the data that the sender intended to send you. So what that looks like, you take your data and your metadata as well. This metadata usually includes information about what you're sending and also about the encryption algorithm that you're using potentially. You take your private key, you create the signature using the algorithm, and then you have your data, your metadata, and your signature, and you send all of those and the public key if they don't have the private key to them. When you verify, you take all of that, and you take the key that you're going to verify with, so public key or private key, and then you pass that to the signature verification algorithm, and it will tell you whether or not that is the signature for that data, for that key. All right, so let's talk about the actual APIs in the browser. So the crypto APIs in the browser. So first, they are available in all modern browsers, of course, except for IE. We'll talk about that later.
It's in modern browsers.
Yeah, fair enough. Yeah, we'll talk about that later. The interface is window.crypto. All the methods are asynchronous, so they all return promises, which is awesome, except for IE. Supports a wide range of formats, so RSA, AES, HMAC, JWK, JSON web keys, Pixie, etc. And it's also performant, at least relatively speaking. compared to third-party libraries. So this is a link here as compared to a study that someone did a few years ago, compared the native APIs versus third-party libraries and the native libraries one-handedly. So what are the supported operations? What can you do with the APIs? You can generate cryptographically strong random numbers. You can generate keys, public and private keys. You can import keys from other systems, and you can export keys to send to other systems. You can wrap and unwrap keys. So wrapping a key means exporting it and encrypting it in one operation. We'll see that later. You can derive bits and keys. You can do signatures, and you can verify signatures. You can, of course, do encryption and decryption, and you can create digests as well. So what are some of the things you can do with these APIs? So you can do end-to-end encryption, you can do secure chat, you can do secure end-to-end file upload, which we'll see later. You can do secure random value generation, so like the node UUID library, when it runs in the browser, it uses these APIs to generate the UUIDs. You can do key binding for things like proof of possession, which we'll talk about later. And you can also do things around other things around authentication, like the OAuth code flow, which is something that I'm working on right now. So here's a complete list of all the APIs. So like I said, window.crypto. For some reason, get random values kind of sits on its own off of window.crypto. And then there's this subtle interface that has all these other methods here, which are basically all things we just talked about. We're not going to go through all of them. I don't have enough time today to go through all of these. As you know, with encryption, you think it's going to take 30 minutes, and 2 weeks later, you're still not done. So we're going to talk about a few of these today. So first is generate keys. So this generates crypto key objects that are used when you need a key to perform other crypto operations. So if you want to encrypt something, sign something, import, export, etc., or export, I should say. So this can return two different things based on the algorithm that you want to use. So if you're doing an asymmetric algorithm, such as RSA, you'll get back a crypto key pair, which is an object, and this is what you see here, line 25. You get back an object that has a public key and a private key property. And if you do a symmetric algorithm, you will just get back a single crypto key object. You'll see here, so how it works is you create this options object that will have the name of the algorithm you want to use, and then algorithm-specific options. So this is RSA Pixie, and then you pass in what hash you want to use, modulus, public exponent, initialization vectors, stuff like that you put in there. You say whether or not you want the key to be extractable. So do you want this key to be, can you use this key with wrap or export to send it to another system? Maybe you don't. We'll talk about that. And then the usages. So you have to declare upfront what you want to use this key for. So I just want to be able to do signatures and verification. You need to declare that up front. If you want to do those in encryption and decryption, you need to say that up front. And then you'll get back, like I said, either a single key or a pair of keys. One thing to note about these crypto key objects is that they're not the actual key material. So you don't just like two-string them and get the key material. You have to use the other operations to do operations with the key. And there's another important reason for this, we'll talk about later. So let's say you have a key that from another system that you want to use in your browser. Maybe you're being sent a public key from your backend that you want, and you're going to encrypt something and send it back to them. So that you use settle.import key. This will import a key from another system, so that can be used in the browser, and it'll give you back a crypto key object that you can use for that. It supports, importing and exporting supports these four formats: raw, PXE, SVKI, and JSON WebKey. So how that works, so here's some pseudocode where we fetch an API, a key from our API. We say what the format of that key is in. We say what is the encryption, or what is the algorithm that the key is using, all that stuff. You declare whether or not you want extractable. You say what you want to use it for, and then you will import key with the format, the key, the options, if it's extractable, and the usages, and you get back your crypto key objects. So you can import keys, and you can also export keys. So if you have, let's say, a public key you want to send to another system, you use that. And it converts the key into a portable format, one of those formats we talked about before, that can be transmitted to another system. So it's rather self-explanatory, where let's say you have a key here, you generate a new key pair, you say what format you want the exported key in, and then you call export key with the format and the key, and you get it back, the key in that format. Here's just an example. If you've never seen what a JSON web key looks like, this is what is basically a JavaScript object, kind of like a JSON web token with claims in it. So I guess the for wrap key will export the key and encrypt the key in the same operation. I'll demonstrate a practical use case of that later. And one neat trick, if you have a key that, let's say you want to generate a public-private key pair, and you want to send the public key to another system, but you want the private key to be not extractable, what you can do is you declare upfront that you want both of them. You have to declare upfront that both of them are extractable, and then you can export the public key and immediately re-import it as unextractable. And now you get the same key material, but it's referenced the same key, but now it's not extractable. And that's because you probably don't want someone to be able to pull out that private key from your browser. Encrypt and decrypt, rather straightforward in terms of what you pass to them. So you say what algorithm you would like, what key you want to use, and what the payload is. It returns back. So here I'm generating a new key pair. I say I want to be able to encrypt and decrypt. You oftentimes with all the APIs, you're using things like array buffers and things like that. So we'll encode the string hello world. That'll give us an array buffer. We'll pass that to the encrypt function with the algorithm and the key. We'll get back an array buffer with the encrypted data, and then we can pass that right back into decrypt if we'd like, or you can send it to another system. So signatures, talked about this before. This is kind of a long example, so we'll walk through this as well. So sign, it will give you an array buffer with the signature that you've asked for. An example, so this is an example of kind of manually creating a JSON web token. So a JSON web token is, like for example, our access tokens at Microsoft are JSON web tokens. They have a header. It's basically a JavaScript object. You see at the bottom, it's a string that has 3 parts separated by periods. The first part is a stringified object that has your header information. So as you see here, it's like what type, it's a JSON web token, what algorithm you're using, things like that. The second part is the actual payload, so this has the actual information you're trying to transmit. Also a stringified JavaScript object, and the last part is a signature for that object. And so how you can generate that is, you've seen, just saw these steps. We'll generate a key, we have our data, we're going to you need to base64 encode these things, so we'll base64 encode the header object, and then we'll do the same thing with the payload, and now we have this string that is the stringified object for the header and the payload, and now we pass that to crypto.settle.sign. We pass in the same options as we did before, so one of the nice things about you saw before when we generated a key, there's this object of configuration options. You can kind of pass that object around to all the different methods that need it, kind of as is, which is nice. And then we'll take, the options objects, our private key, and then the data that we want to encode, and we'll get back a signature. And then we can append those all together and send those out the door to whatever system needs it. And then verify. This does the verification. So verifies a digital signature, and will give you back a Boolean true or false. So this is kind of going through the process of taking a JSON web token, breaking it apart, decoding it, getting our key, importing it, and then passing all of that to the verification algorithm, as you can see here. All right, I11. If I've learned anything about after working at Microsoft for 6 months, it's that IE11 is still very much a thing. So, IE supports crypto operations under window.ms crypto. And that's not the only MS prefix crypto library that we'll talk about today. So instead of promises, so IE11 doesn't support promises out of the box, you get back crypto operation objects. And as you see here, you can attach events to these objects, such as complete an error. The MS Crypto interface supports almost all of the methods, algorithms, and formats as Windows.crypto. There's a lots of subtleties here in terms of like Windows 7, IE 11, sometimes the get random values method just doesn't exist. Export key is like an example where in other browsers, if you ask for a JSON web key, it'll just give you a JavaScript object, which is what you expect. IE 11 will give you an array buffer. So there are little things like that. But most of the time, the method signatures and return values do match. If you want to write a function, so like what I did in my code was I wrote a helper function that kind of abstracts all that away, and check to see is MS Crypto in this browser. If it is, I'll manually construct a promise, manually call resolve and reject on that promise with the events from the crypto operation. As you can see here, you attach these event listeners and you call resolve with the values that are coming back. Okay. So now let's talk about some practical usages of these APIs. So the first is MSRC, which is the Microsoft Security Response Center. And MSRC is, the mission is to protect our customers from security vulnerabilities in our products and services. So it's responsible for the bug bounty program at Microsoft and Patch Tuesdays, which I was told explicitly to put in here because apparently it's a big thing. Provide secure channels for disclosing security vulnerabilities in our products. Another thing is that they are going to be hiring JavaScript people soon. So feel free to reach out to me if you are interested in that. I can forward you along. One tidbit I'll share on that is that this is not like a stock photo. This is an actual building at Microsoft. It looks like that, I was told. At Microsoft, you can like get into any building pretty much, but not there. I can't get in there. You need special access. So if you want to be able to go in there, like the super cool building from like CSI and stuff, you can. Really cool team. I used to work with the principal engineering manager from the team. Awesome guy. So if you're interested in this sort of stuff, definitely let me know. MSRC.Microsoft.com is their website. So they have a security portal, MSRC Researcher Portal, and Microsoft accepts vulnerability disclosures through this portal. It's available on /create-report. So the portal uses the browser crypto APIs to encrypt the attachments in your report and send them to a secure backend environment where they are decrypted. This is because this is where researchers oftentimes will upload proof of concepts or weaponized exploits of our products. And so it is paramount that these do not get in the hands of someone else, right? We can't afford to have someone hack the website or do whatever to get that code, right? That is like super important for us. Because when we get hacked and stuff, it makes the news, right? So this is extremely important for us. So how do they do this? Let's talk about some end-to-end encryption in the browser. So we've talked a little bit about, I mentioned wrapping keys and things like that. So this actually combines a few different things: asymmetric encryption, symmetric encryption, wrapping keys, all in one. So first thing that they do is they retrieve a public key for their backend service, from their backend service, and then import it into the browser. That's this first part here, the first 10 lines. They then generate a new private key. They generate a new private key to encrypt the uploaded file. So they send a public key to the browser, but they don't actually use it to encrypt the file. They generate a new private key, which they'll use to encrypt the file. They'll use the random values API to generate an initialization vector for the algorithm that they're going to use. They then encrypt the uploaded file with the private key that they generated, and then they also prepend it with the initialization vector. This is just a convenient way to send the initialization vector and the file together to the backend, because the initialization vector is needed to decrypt the file later. Then they wrap the generated key used to encrypt the file with the public key from the backend. So instead of using the public key from the backend to encrypt the file, because that's slow, asymmetric encryption is slow, and you can imagine these are potentially huge projects that are being uploaded, we use the public key to encrypt the private key. So we're just encrypting we're just using that to encrypt just the key itself. And then we send The wrapped key, so again, wrapping a key exports it and encrypts it. So we have an encrypted private key and an encrypted file with the initialization vector, and those are sent to the backend. And in their backend, they split apart the initialization vector of the file, they decrypt the private key, then they use the private key to decrypt the files. So like I said, kind of cool stuff, super high impact if you're interested in this stuff. And then lastly, Microsoft Authentication Libraries. This is what I work on in Microsoft. So we kind of joke that our job is basically to get you to this screen. You've probably seen this screen a lot every day, sometimes annoyingly too much. Sorry about that. You can post issues on our GitHub. Yeah, it's we joke that we just build URLs all day. Our job is to build URLs and send you to those URLs. It's not much, but it's honest work. So the Microsoft Authentication Libraries, they're a set of open source SDKs that allow developers to integrate with our identity services, such as Azure Active Directory. It isn't just for JavaScript, it's for C++, C#, Java, Android, the Apple products, etc. Basically all of the, I guess not all of the Microsoft products, but many of the big Microsoft products use our SDKs, and there's an effort ongoing to move all basically Microsoft to our SDKs. So common usage is to acquire access tokens, which take the form of JSON Web Tokens, which we talked about a minute ago, to use with secure web APIs such as the Microsoft Graph. So if you've used our library before, it was potentially because you wanted to get information about someone's calendar or something from Teams or something like that. And so you'd acquire an access token from us, and then we'd give that to you, and then you would send that when you request information from Microsoft Graph. And msalt.js, which is what I work on, is intended for web applications and implements the OAuth implicit flow. If you're familiar with the OAuth flows, you can check out our GitHub, akms /msalt.js. So let's talk about OAuth. This is kind of very, very simple explanation. It's more complicated than this, but this is a very high level what's going on. So your web application determines that it wants access from a protected API, let's say the Microsoft Graph. You call the Microsoft msalt.js and one of our APIs, and we send your user to the Microsoft login UI, which you just seen, where the user enters in their credentials, proves that they are, does multi-factor authentication, all that stuff, and provides consent. So yes, I want Teams to be able to access my email or whatever it is. When you're done, Microsoft, the login UI will send the user back to your website and will include an error potentially, or will include an access token which proves that you've logged in and that contains the information about what you have access to. Then your web application now sends a request to the API, let's say Microsoft Graph, and includes this token. And Microsoft Graph knows how to validate these tokens. So there's a fundamental flaw with OAuth in this regard, with access tokens in this regard, which is that if an access token is somehow lifted from the browser or whatever system it's on, the protected API has no way to know if the device that's using the access token was the device that the token was issued to. So if the token was issued to me in my browser, and you've written a nice Chrome extension that steals that stuff somehow and sends it to you, you could use it and pretend to be me, in theory. So because of this, we have short-lived access tokens for only 1 hour. So that way, if you do get your hands on access token, you have 1 hour to do things with it before it's going to expire. Now, if you think about Microsoft scale, we deal with billions of requests a day. That's a lot. That's many, many access tokens that need to be minted every hour. And that's expensive. So we like to not have to have access tokens that live for only an hour. It would be cool if they could last for 24 hours or something like that. But because we can't guarantee what we just talked about, they have to be short-lived. So the feature mitigation, and what we're working on now, is key binding via proof of possession. So what is proof of possession? So this is based on an IETF spec. There's links at the end if you want to read those, in addition to specs for the crypto APIs and things like that. So here's how proof of possession works if we think about the flow I just described. So the web application determines that it wants access from a ticketed API. You call the MSOL APIs, and then now first thing MSOL does is it will generate a public-private key pair in the browser for the request. This key pair will be unique per resource and HTTP method that you're using. The key is securely stored in the browser, and the public key is sent to the Microsoft Login UI with the request to have you log in. MSOL sends the user, so MSOL sends the user to Microsoft's Login UI where the user enters their credentials like we just talked about. The Login UI sends the user back to the application with a new access token. And now the public key that was sent in the request initially is included as a claim in this new access token. So now we've been given back a new access token, and the public key that you used is inside of that. That's kind of like a clue for us to know what to do next. This token can be cached on the device. So now what MSOL does is it will retrieve the private key that's stored earlier, that created earlier, and uses it to construct a new JSON Web Token. So we have like a Russian doll situation going on here, where we have a new JSON Web Token, which includes the entirety of the access token we just got as a claim inside of it. And then we sign that with the private key from the initial request as it gets sent out the door. So we hand that back to the application. The web application then sends a request to the protected API with this signed JSON Web Token. It's a JSON Web Token with another JSON Web Token inside of it. And also has the public key inside of it, and it's signed with the private key. Then the protected API basically cracks open all these tokens, and it decodes the JSON Web Token, verifies that it was signed with the private key for the corresponding public key that was included in the access token. So if that all fails, then we know that you weren't the one, you signed this with the wrong private key, basically, or you manipulate this data. So that is what we're working on that right now. We're prioritizing having this work for our first party Microsoft products, but it'll be available at some point in an upcoming MSOL release. And like I said, this is based off open standards, so you could implement this in your own applications if you wanted to. If you create your own access tokens, you could implement this as well. The spec is in draft form still. We're working against what's out there at least. Okay, so some learnings and advice. So first, it's for all of this. So it's helpful to have an understanding, familiarity with the cryptography fundamentals, the things we talked about at the very beginning. It's worth your time if you haven't done any of that stuff to go through that exercise and learn about those things. It'll help you understand what's going on. As well as JavaScript things such as promises, array buffers, typed arrays, because oftentimes, for example, all these APIs seem to work with array buffers. So if you're dealing with JavaScript objects, you have to stringify those objects, turn them into buffers, then like do that song and dance again when you get an array buffer back. So things like that are kind of annoying if you haven't done them before. And it's always, all these things tend to be pretty opaque, right? You see an encrypted value that you've console logged and like, that looks okay. You don't know until you actually try it, whether or not it's right. So on that note, go slow and be patient. If you go to the MDN page, there's a big box with a warning on it that's like basically like, if you're not sure if you should be using these APIs, you probably shouldn't be. Which is, it's like the only warning on the entire MDN site, I think. And it's fair, these APIs and doing cryptography stuff like this is hard, but I see that, for me, I saw it as a challenge. I think you should too. Don't think that you have to be senior or whatever to work with these things. You can grow a lot by tackling hard things like this. So another thing, kind of like a strategic thing, check which crypto interface the browser supports and fall back gracefully. So check whether or not you have MS Crypto or not. And either, if you don't have the crypto API, fall back to MS Crypto if it's there. I'll talk about an even farther fallback if neither of those work. This is just kind of a general thing. programming-wise, but build your own abstractions. So centralize all your window.crypto code in one place. So that way, if you want to change, the algorithm you're using, or even the entire implementation of how you're doing your crypto stuff, it's much easier when it's all in one place. This code is hard enough to deal with on its own, so centralizing that in helper classes or whatever it is will make your life a lot useful. A lot more, will help you a lot. So, talked a little bit about storing these crypto key objects. Like I said, they're not the actual key material, and it is not recommended that if you want to store these in your browser to use them later, like you want them to persist between page loads, don't export them and then stringify them and put them in local storage. That's not good. What you should do is use IndexedDB, which is an asynchronous database for the browser that is specifically built for things like this, where you can give it blobs and files and things like that, and it doesn't only handle strings, it handles all sorts of JavaScript objects. And so use IndexedDB to store those crypto key objects if you need them to persist between payload or between refreshes and page loads. And then lastly, be mindful of performance, especially on mobile devices. So we talked about how these APIs are performant relative to third-party libraries, but they're still expensive operations. So if you're encrypting a large video on a mobile device, that's probably going to be pretty slow. So be mindful of that and build your the experience for your users accordingly. Lastly, here's a bunch of links to the spec. If you're bored on a Friday night, you want to read some W3C specs, it's there for you. The MDM docs are awesome. I basically use these exclusively. Like I said, the MS Crypto docs are a little bit harder to find, but I've got a link here, aka ms/MS Crypto. So like I said, MS Crypto isn't the only Microsoft crypto library available. I discovered this week that Microsoft Research put together MSR Crypto, Microsoft Research Crypto, which is a fully featured, self-contained encryption library that does basically all these same things. They kind of recommend that you don't use it. They recommend that you use the browser APIs if possible, but it is a potentially good fallback for certainly if the crypto libraries aren't available, but they might be more appealing than the MS Crypto libraries because MSR Crypto supports promises, even I11 through polyfills and stuff like that. So potentially we're checking out. And like I said, the proof of possession IETF specs are here if you're interested in that, and the links to MSRC and to MSOL are whatever you go. That's it. Thank you. Yeah.
And so one of the steps was in the public and private key. You mentioned in the OAuth flow that if someone gets access to the access point, you can start impersonating the person. Couldn't you also have a malicious extension that grabs the public key and private key and does the same thing?
Yes. Yeah, so the private key specifically is what we're concerned about here. Right? We don't see any of the private keys. That's one why when we generate the private key, what we'll do is I mentioned in there how if you create a key pair, when you say if you want to be extractable, you can't say per key whether or not you want one of them to be extractable and not. They're both extractable by default. So you'll get a public key that's extractable and a private key that's extractable. So if you want that private key not to be extractable, you export it and then immediately import it but set extractable to false. So it'll give you the same key, but now it's not extractable. Now, that's the first mitigation. Now, yes, well, even if you do that, someone could dig into your file system and find the bits for that and all that kind of stuff. There are lots of things that we're working on solving. That is one of them that we don't necessarily have an answer to. So not going to be perfect, but we'll do as much as we can certainly to protect against things like that.
But that's still harder than if it was just an access token sitting in your browser.
Right. Yeah. Yeah. The bar is still much higher. Yeah. Yeah.
So most of the time when I've dealt with authorization, I've always used OAuth or some other service. What do you think would be the main use case for me actually getting into the crypto libraries and signing things? What do you see as the main use case for actually using those APIs?
Just generally in one of your applications or in the context of authorization specifically?
Oh, I'm just saying that I mainly think about these APIs in terms of authorization and authentication, but what other uses or reasons why I have to check these things out?
Yeah, I mean, I think end-to-end encryption, I think, is a really compelling one. So if you build a chat application, it seems like every social app nowadays has chat, right? We worked on that at my last job. So that's a really compelling reason. Or end-to-end file uploads, things like that. Those certainly are the two that immediately come to mind that a company might actually want to do. Now there's other ones in terms of generating UIDs and things like that, which is a little more unlikely that you'll do that. But I think the end-to-end encryption is probably the most compelling for most companies.
Thank you.
Yeah, Patrick.
Why do you have to specify the usage?
Say that again.
Why do you have to specify the usage?
So the question is, why do you have to specify the usages of your keys? And that's kind of the phrase I'm looking for. It's like minimum access level, right? So you only give your users minimum level of access that they absolutely need to do their job. You kind of treat your keys the same way. If you're only going to use it to verify a signature, don't let it also encrypt things, because if someone were able to steal it or something, if it were compromised, you wouldn't be able to someone do something with that, right? So I think it's just following that ethos. All right, feel free, if you have my emails and stuff was, my email, Twitter and stuff was on the front, jason.r@microsoft.com. If you have questions about this stuff, questions about working at Microsoft, Azure, open source it, Microsoft, or if you're interested in those MSRC openings, let me know. Thank you.